Now in this video lecture we'll design the band brakes. Normally we have three types of band brakes. The very first one is simple band brake, second one is differential band brake, and third one is block type band brakes. But before we go for this, we will cover up some basic theory. Consider here a drum of radius equal to r, and we wrap a band over this. If we wrap the band over this, there is a friction occurs between this point of contact here to this point of contact, and if we try to pull on this side, naturally the friction force will act in the opposite direction. This is friction force, so this tension must be more as compared to this tension. So this side we write T max and this side we write T minimum. Your contact starts from this point and the contacts end at this point. So this angle is called as theta and is called as angle of wrap. Theta is called as angle of contact or angle of wrap, and normally is taken as in radian. 1 degree is equal to pi by 180 radian. So the contact starts from this point to this point, so this one is called as angle of contact. Then it is known here that a relation between T max by T minimum is always given by e to the power mu theta, where mu is called as coefficient of friction here between the brake and the drum. T max is the maximum tension and T minimum is the minimum tension. The braking torque is obtained using the equation. So here the drum is rotating in anti-clockwise direction, so braking torque is done in the clockwise direction. So this force multiplied by radius r will be the clockwise torque, so I will take it positive, and this tension multiplied by this distance will make it anti-clockwise. So braking torque is always given by r multiplied by T max minus T minimum. So normally equation number 1 and equation number 2 are commonly used, and the braking torque you can obtain from the braking power, and braking power is given by 2 pi nt of brake power of braking divided by 60, where n is the rotational speed, Tb is the brake power, brake torque, and P is the power consumed in braking. Now we'll design the simple band brake. Simple band brake. We will discuss in this video how to design the simple band brake. In the simple band brake, we have a hinge here to the lever. This one is a band which is wrapped over here, is attached to this point. External force is applied here, is equals to P. Let's say this distance equals to A. Let's say this distance equals to L. This one is the diameter D of the drum. Assume that the drum is rotating in a clockwise direction. If the drum will rotate in a clockwise direction, the tension here will be in the opposite direction. So this is the T max, and this side we have a tension equals to T minimum. This is the contact angle theta. In this case it equals to pi. It can be different for different arrangements. So parameter involved in the design is T max is the tension on tight side, that is in Newton. T minimum is the tension on the slack side in Newton. Theta is the angle of wrap in radians. Mu is the coefficient of friction here. D is the diameter of the drum. In the last lecture we already derived the equation, that is T max by T minimum is equals to e to the power mu theta, and the braking torque is equal to T max minus T minimum multiplied by the radius of the drum, that equal to d by 2. So at point O we have a hinge, so we have two reactions here, one is OX, one is OY. This tension is T max is upward direction, this tension T1 is upward direction, and the force is acting in downward direction. If we take the moment of all forces about O, so total sum must equals to 0. All these three forces are passing through point O, so they will not cause moment. T minimum will cause anti-clockwise moment and P will cause a clockwise moment. So P into L minus T minimum multiplied by A must equals to 0. So P is equals to T minimum multiplied by A divided by L. If the direction of this drum is reverse, that is instead of the clockwise, if you make it anti-clockwise, the tension T max and T minimum, that is this tension T max and T minimums will exchange their place, that is T max will come to this side and T minimum will come to this side. In that case, it is observed that the braking, for the same braking torque, that is the previous case, a larger force P required to operate the so we have a same hinge here O. This is same reaction. We have same reaction here equals to OX at the hinge. This is reaction equals to OY at point O, but the position of T max and T minimum is reverse because it is a counterclockwise. So this is T minimum and this is T max. This distance is A and this distance equals to L, and this is the external force applied to operate the lever equals to P. If I take the moment about all forces about point O, then total moment must equal to 0. These three forces are passing through point O, so moment will be equals to 0. P about point O will make a clockwise moment, so this is P multiplied by L, and T max about point O will move in anti-clockwise direction, so this is T max multiplied by A is equal to 0, or P is equals to T max multiplied by A divided by L. If we compare this term and this term, you observe that external force P is a simply function of T minimum in the first case, that is the drum is rolling in a clockwise sense, and in second case the T max, the function of T max is always greater than T minimum, so if the drum is rolled in an anti-clockwise direction, we require more force for the same braking torque. In the simple band brake, we do not have a condition of self-energizing as well as the self-locking property, so there is no question of self-locking and self-energization in the case of simple band brakes. Now, as per the design of the band brake is concerned, let T is represents the thickness of the band brake, which is normally taken as 0.005 times D, where D is in mm, the diameter of the drum. Sigma D is the allowable tensile stress in band in Newton per mm square, and W is the width of the band, which is in mm. So we know that T max is equal to sigma D, that is the design value, multiplied by T multiplied by W. So we can calculate the width from this, that equal to T max divided by sigma D multiplied by T. The second type of band brake is called as differential band brake. In differential band brake, the two ends of the band are attached to the lever at distance A and B from the fulcrum, that is from the hinge. This I will show you now. So here this is the drum and this one is the lever, this is a single piece, and this one is the drum and this is lever, again a single piece. We have a hinge here hinge at this point. Let's assume that the drum is rotating in a clockwise direction. This end is the distance equals to, let's say, A, and this distance equals to B from this point to this point, and this perpendicular distance is always make a 90 degree to this side. Here also this makes a 90 degree. Let's say this distance equals to A, and let's say this distance equals to B. So in this case B is more than A, and in this case we assume A is greater than B, and for this case B is greater than A. If the drum is rotating in a clockwise direction, this is the position of T max, and this is the T minimum position, and if the drum is rotating in this direction, in the same clockwise direction, this is still a position of the angle of contact starts from here. The angle of contact end at this point. This angle equals to theta, called as angle of contact. If we have a situation where this length, that is a free end, that length is A and this length is B, and if we have A greater than B, then the force F must act upward. We will prove this. And if B is more than A, then the force F must act in a downward direction. To analyze this now, we assume that this is just acting perpendicular. We will neglect this angle. For simplicity, I will neglect this angle and I will take this value equals to perpendicular to the board. Later on we can modify this value. Let's say this is T minimum acting at distance B from point O, the hinge. This one is T max position, and this distance equals to A, and the force F is acting vertically upward from this point. This distance is L, this distance is B, and this distance is A. If I take the moment about point O, which must be 0, so this F into O, F, the moment of F about O is anti-clockwise, moment of T max is clockwise, multiplied by distance A. T minimum will make anti-clockwise moment, F will make anti-clockwise moment, and this must equal to 0. So F into L is equal to T max multiplied by A minus T minimum multiplied by B, or F equals to T max multiplied by A minus T minimum multiplied by B divided by L. So what you observe here is that this force is T max multiplied by A minus of T minimum multiplied by B divided by L. But suppose this force is acting in a downward direction. So if the force is acting in a downward direction, so here also this is acting in downward direction. In that case the moment caused by this one is positive, and if this moment is positive, then this value is minimum and this value is positive. This value is minimum and this is minimum minus value, and this is positive value. So probably the answer of F will be negative, and therefore whenever we have A greater than B, the force F must act in a upward direction, not in a downward direction. So always remember, if the length of this free end is more than the other end, then the value of the force must act in the upward direction. And if we have a different situation where this length is more than A, then F must act in a downward direction. Let's check this time what will happen. So we have again the same direction, that is equals to F. This is T max, this is T minimum, acting in the opposite direction of the rotation for the drum. So if I take the moment about this point now, that is point O, that is a hinge, this sum must equal to 0. So moment of F about point O is a clockwise, multiplied by the distance equals to L. The moment of T max is also clockwise. And moment of T minimum will be anti-clockwise. So if you solve this equation, we will get F equals to T minimum multiplied by B minus T max multiplied by A and divided by L. Since B is more than A, there is a chance that this value of F may be positive. So you just remember one thing, that if B is greater than A, it should be downward, and A greater than B, then F is upward. Now we will continue this analysis, and we have got here F equals to T max can be written as T minimum multiplied by e to the power mu theta multiplied by A minus T minimum multiplied by B, and whole thing is divided by L. So we can take out T minimum common, even L is common. What is left is A times e to the power mu theta minus B. Now from this equation we can conclude here that the sign of F depends on this bracket. If this bracket is equal to 0, then we don't require any type of force, that is called as self-locking. Or if we have this bracket is equals to negative value, then the direction of force is acting in a downward direction. So that becomes the condition for self-locking. So for self-locking, A into e to the power mu theta minus B must be less than 0. In that case, this value is negative. You have to apply the force to disengage the brake. Or we can say A into e to the power mu theta is less than B. And whenever this value is positive, in that case the F will act opposite, and this value, that is T minimum minus B, always subtracted from this value. That is called as self-energizing condition. So for self-energizing, A into mu theta must be greater than B. Now if you want to analyze the drum in the anti-clockwise direction, so what we have done in simple band brake, we have exchanged the position of T max and T minimum. So same thing is done for the differential band brake also. So this position will be replaced by T max and this position is replaced by T minimum. And we can continue the analysis for the lever then, and we get the almost same equations. Only thing that instead of T max, it will be T minimum. The third type of band brake is a band shoe brake. It consists of shoe plus band. I will just explain this with the help of figure. So this one is a drum and this one is a band. We have a fulcrum here, and the external force is applied in upward direction. In between the band and the drum, we have band shoes like this. So we have n number of band shoes. So this one is called as drum, this one is called as shoe, this one is a band. N represents number of shoes. The difference between the simple band brake and the band shoe type brake is that the angle of contact is not everywhere, and therefore this equation, that is T max by T minimum equals to e to the power mu theta, is not a valid equation. We should not use this equation for this one because the contact is not continuous. So here this E shoe makes an angle of contact equal to 2 theta. In that case, we have to modify the equation. T max divided by T minimum equals to 1 plus mu times tan theta upon 1 minus mu tan theta. This is for one shoe, and if we have n number of shoes, it will be given by to the power n. So this is the only difference between T max and T minimum. Let us assume that the drum is rotating in a clockwise direction. In that case, this is the value of T max, and this is the value of T minimum. So procedure will remain same. So again I take the moment about the hinge O equal to 0. So this P about point O will make anti-clockwise moment, distance equals to L. T max will make clockwise moment. Multiplied by A, and this is passing through point O, so that equal to 0. So P multiplied by L, so P is equals to T max multiplied by A divided by L. So naturally this position of P, if we have in a right downward direction, or the drum is rotating in the anti-clockwise direction, then P should be upward, and if it is rotating in a clockwise direction, then it should be downward. Then only the value of this will be less.